Hello grade 9s, we're going to move into our second topic in our unit on electricity, which deals with circuits. And so we have this little circuit board diagram up here, or a picture of a circuit board, and to me it kind of looks like a little city. There's some little pathways, there are some parts of it that are accepting the electrical load, and so I kind of think of the streets as like these areas where the electrons can flow, and what they're being used for, what their job is, kind of relates to a city as well. In a city, various jobs need to get done, and the same thing could be said about a circuit as well. And so we just talked about static electricity, and some of you were able to come up with some positive uses for it on your assignment, but current electricity is a lot more useful. Static electricity can be unpredictable. We can get discharges when we don't want them. Charges can build up to dangerous levels for sure. And so if we can regulate this a bit more, if we can create this steady flow of electrons with a steady current, it's going to be a lot more useful to us. And in fact, this is the type of electricity that we're normally using in our homes today. Okay, so in order to have a circuit, there needs to be a path for these electrons to flow. The word circuit kind of relates to the word circle. Needs to go around and around, we could say, in a way. And so these electrons are doing the same thing. They need to start at one point, follow a path, and then get back to their original source. And so typically for our pathways, we're using wires as conductors, made up of materials like metals, which we also talked about in chemistry and a little bit in our last topic. Metals provide the most efficient ways for electrons to travel and flow in our everyday life. Okay, so we need two things in order to make these electrons flow. We need some type of energy source, and we need their pathways, the circuits or the wires, or however you want to think about it. Circuits are going to have four key components in them. They're going to have a source, typically some type of battery or cell, that's going to provide us these energized electrons that can move. We're going to have some conductors, the pathway, for those energized electrons to travel around on, let's say. Switching mechanism, maybe similar to your light switch. In some cases we need, well, maybe in a lot of cases, we might not want to use, we don't want to use lights all the time. We need some way to turn them off. We need to disrupt that flow of electrons when we want. We want to have some control. So that's the main thing there. And a load. So we're creating, or we're using electricity to hopefully make our lives easier. There is some type of job or function to all of our electrical devices, and that relates to the load. It's what is that electrical device going to do? And so here's an example of an electrical diagram that we might be asked to draw. It has a couple key features. Here's our load or battery, or sorry, this isn't our load, this is our cell or battery. In this case, it's more accurately called a cell. Electrons come from the negative end of our cell, which is also called our anode in some cases, and begin following this path. Here's our load, represented by this circle with an X, which is our light bulb. These straight lines here represent our conducting wires, and we got a switch here as well. So there's a couple things when drawing these electrical diagrams that we want to keep in mind. Number one, we want to use a pencil and paper, maybe similar to math. If we make an oopsie, we want to make sure we have the ability to correct it, and a pencil is the best way to do this. Typically, our wires form some type of rectangle with the corners meeting at right angles. Kind of mentioned that already there. We don't want to cross conductors. That would create some type of short circuit, so we definitely don't want to do that. And we want to be as neat as possible. And so there's a section in your textbook in topic 2 which outlines all the different components and symbols that you will need to know for drawing circuits. So, sorry I'm not going to be following all the rules, but because I'm not using a pencil, but I will try and do an example on the board. So to draw a circuit diagram for a simple light system, it has two 1.5 volt cells. So I might start with that first. A cell kind of looks like this, a big line and a small line, where the big line represents the positive end of the cell, the small line represents the negative. So I want to draw two of these. And as we're going to find out, if we have two or more cells, we actually have made something called a battery. Now we need some conducting wire, so I'm going to draw these with a ruler. And then I need some other components as well. I need a lamp. So as we saw in the slide before, it might look something like that, a circle with an X through it. And I also want a resistor. So resistors just look like this. Again, there's a page in your science textbook that has all the different components. You don't need to memorize them for now. And a switch. Our switches look something like that. And that is just a quick example of how you might draw a circuit diagram. So it's really important to read the question, what is it asking for, and then include those components in your diagram. Okay, so once we get the steady flow, that is what we call electrical current. We're going to measure it in amps. How much current is flowing relates to amps, and its symbol is I. There are other instruments that we could use to measure how much current is flowing, but typically for us we'll just use something called a multimeter because it can measure voltage, current, and resistance. Maybe another common question that comes up is why is the symbol an I if we're talking about current? Usually our symbol kind of matches with the first letter of the word. Why isn't it a capital C? It's actually from a French word, intensity, which resembles the word intensity in English, and so kind of relating to the intensity of flow. So just like in a big huge river, if we look at something called the North Saskatchewan River, there's a lot of water flowing, so that would have an intense amount of flow, and maybe we measure that in like liters per hour, or second, how many liters are flowing past a certain point every second. And then if we look at something like the Sturgeon River, which is much smaller, it's going to have much less current. So in the same way, some electrical devices are going to have a large amount of flow, a large amount of electrons flowing, and some are going to have much, much less. Okay, potential difference. This is just another way of saying voltage, kind of describing the energy per unit charge that these electrons have. And it's kind of in relation from one point in a circuit to another. It's measured in volts, capital V, and we could measure it with a voltmeter, but I don't have one. like I said before, all we have is this multimeter, but it measures everything, and so that's typically what we use. And so, yeah, if you look at maybe some of your batteries at home, typically they're 1.5 volts. That's the energy that they can supply. Okay, there's some different types of circuits as well. This style is a parallel circuit, and it has, so if we just look at this first square right here, we have our cell, and it's supplying some electrons to this load, but we've kind of added like another branch on, so we can add two light bulbs to one energy source. So there are some advantages to having this style of circuit. The main advantage is that if we get a break in the circuit right here, this light can still stay on. So typically what we see is if there's a break in the circuit, if it's just in one big if it's all in one big rectangle, if it's interrupted at any point, that's going to disrupt the flow of electrons, and any load that's on there is not going to be doing its job. So our houses are wired this way, so that way if there's a break in one part, we can still use electricity in other places. Okay, kind of like we already talked about, we can compare the flow of electrons to the flow of water. And so energy is going to change as it is moving from place to place. So looking at this part of the diagram right here, we have this reservoir, it's a container full of water, and it's going to have the most energy here, and it's going to be losing its energy as it moves downhill. And so our highest energy point is here, our lowest is going to be at this point right here. In the same way, we also want to be able to control the flow of water, and so that's why, excuse me, we have this like little valve right there, so we can turn it off. Maybe there's a lot of water right here. This container's not as big. If this one fills up, we don't want to make a big mess, have it spill over, so we can use that control to stop the flow of water. And so in a very similar way, we have the most energy. Our electrons are going to have the most energy at this point here, and the least as they get to this point. And this controlling mechanism is comparable to this as well. Is comparable to this switch right here, where we can shut the flow of electrons off if we want. We have this pipe here, which allows the water to flow. That's comparable to our conducting wires. And we have a load. So this water is doing a job. It's turning this water wheel. This is comparable to our light bulb here, which is our electrons. The energy from these electrons are being used to power this bulb. In the same way, the energy from this water is being used to make this water wheel spin. That's all for now. I'll post an assignment for you. Take care.